Alright, so hopefully everybody has turned in their PA5, which means you're done with programming assignments for this course, and probably for the whole CS sequence, and probably for all of Clark, which is probably feeling pretty cool. So I will grade these over the weekend, but just from the people that have been coming to office hours and that I've been helping with on this, I'm really excited. I'm seeing a lot of light bulbs going on, right? And that's what this is about, is sort of making those connections where we know like the pieces and we figure out how to start putting those together. It's an ongoing process. It continues, next year and the year after and beyond school, but I'm definitely seeing that happening with more and more people, which is really cool. So I'll get PA5 graded and get some comments back to you. And if you've got any questions, you can definitely let me know. If you aren't happy with where your project ended up and you want to figure out the last details, we can definitely talk about that too. So SLPs are due next week, right? And there's a report and there's a presentation that you're going to make and post online. And again, if you don't want that that video to be public, just make an unlinked, unlisted link and send it to me. And then, in your introduction, you're supposed to say whether or not this can be distributed publicly, so just make sure it's clear that you don't want that to happen. So SLPs coming in beginning of next week, and then final exam will be a week from Monday. So, and then we're done. So definitely down to the end of all this. Any questions, lingering concerns with PA5, threads, sockets, all of that stuff? We're going to keep talking about threaded programming today, but from a sort of higher level perspective. All right, so let's talk more about this notion of multiple processes. It's a topic you'll do more in future courses, but I want to talk about some of the other things that can happen. So we looked in some detail at 2 or 3 threads accessing the same area of memory, and the danger if you don't control that access, if you make things what I call non-atomic. And this is something that comes up in a lot of different contexts. For example, we looked at hash tables and hash maps when we were looking at data structures. And if you look at a hash table, it makes this comment down here. Hash table is synchronized. If a thread-safe implementation is not needed, it is recommended to use a hash map. Okay, hash map, if you look at it, will warn you that hash maps are not thread-safe. Okay, so thread-safe basically means if you have 2 or more processes, threads, hitting on the same object, do you have to control that access yourself? A hash map, you have to control that yourself. So what can happen? You can have a, let's think about a linked list, right? So here's, an ant, and here's a cat, and here's a dog. And suppose process 1 wants to add a bat to this list. So you're going to create a new node, and you're going to come through here, and you're going to look at where this node is pointing, and you're going to set this node to point to that, and then you're going to change ant to point to bat. And suppose that while that is happening, another process starts running and comes in and decides to delete cat. And so that thread is going to say, okay, let's look at the node before, which is ant. Let's have that point where cat is pointing, and then let's release this from memory. And now the first thread continues, and it says, okay, yeah, I already made bat point to the new node. Let's change ant to point to bat, and we're done. And your linked list looks like this now. Ant points to bat, which points to an invalid memory location. Right? So that would be a non-thread safe set of operations, right? And some data structures take care of this for you. They would automatically prevent, say, someone from modifying the thread while somebody else was, and some don't. So hash maps, for example, don't do that synchronization. Hash tables do. Hash table, everybody can access it however they like, and it will take care of preventing those kinds of issues. And again, you know, it's atomizing operations. It's saying, okay, this process of find the node you want to insert before, change your pointer, have the previous node point to you. If that's atomic, that cannot be interrupted, right? Then you can't get into that kind of situation where partway through one of these nodes changes and your pointers end up invalid. So that's one whole set of possible issues. Another set of issues is deadlock or livelock. Okay, here's the standard real-world example of deadlock. You're walking down the street, and somebody else is walking down the street directly in line with you, and you come up in front of each other, and neither of you wants to move. You're each waiting for the other person to move so you can continue. That's a deadlock situation, and you will stay there forever. Okay. The livelock situation is the more common one. You have an algorithm running in your head which says, if I'm walking down the street and somebody is in my way, I'm going to move to the side. And so you move over. Well, guess what? They're running the same algorithm and they move over. And now you're facing each other. You can't go forward. So you apply your algorithm again and you move over and they move over, right? And it's not deadlock in the sense that the system is stuck. The system is changing state, but the overall status of the system is not advancing, right? You're not getting any further down the road. That's a livelock situation. And these things happen in computer science, but they happen a lot walking down. So, yes, so yeah, you're not thread safe. It's a good way to think of it. That would be a good t-shirt. That would make all kinds of people wonder. So deadlock and livelock, right? These things happen, and they can happen in programming. So one example we talked about a little bit the other day was sharing a printer, right? And if you were waiting for both a printer and a scanner, and I've got the printer and you've got the scanner, we're never going to release our resources because we need them to do what we're trying to do, but we can't get the other resource that we need because somebody else has it, and they're not going to relinquish it. And so, you know, in that case, these two processes would hold those two resources forever, and nobody would ever be able to use the printer or scanner until you reboot the machine. And so in the 50s, people started looking at this and trying to understand how to manage these shared resources. And Dijkstra, who we did not get a chance to talk about in CSE 215, unfortunately. But Dijkstra is known mostly for like Dijkstra's algorithm, which was a way to find shortest paths through certain kinds of graphs, but he's done a lot of stuff. One of the things he did was he explored this question of shared resources and handling multiple threads. And so he posed a theoretical situation which is called the dining philosophers problem. So dining philosophers, you'll probably encounter this down the road in other courses again. So here's the setup. You have 5 people, and they are sitting in front of an infinite bowl of, could be noodles, could be rice, depending on who you talk to, but some sort of food, right, with an unlimited supply. And there are 5 chopsticks situated in between each pair of philosophers is a chopstick. And philosophers do two things. One, they eat, and 2, they think. And that's a pretty good job. So, to eat, what do they need? They need a pair of chopsticks. Okay? And they can only take the chopsticks that are on either side of them. They can't reach across and take someone else's chopsticks. So a philosopher will pick up a pair of chopsticks and eat for a certain amount of time. And then when they're done eating, they'll put down their chopsticks and they'll sit there and they'll think for a certain amount of time. And the amount of time that they'll eat and that they'll think can be considered to be random. It's not a fixed amount. It could change from instance to instance. And so the question is, how can these 5 philosophers, what rules can they come up with to ensure that nobody starves and everybody gets a chance to eat? And it's a basic resource problem, right? So 5 threads, that's the 5 philosophers, and 5 things that are being shared among them. And each thread, each philosopher needs these 2 resources. Well, this resource is also needed by this thread, which also needs this resource, which is also needed by that thread. Okay, so there's a sharing question. And so you can start to cobble together some algorithms. For example, pick up the chopstick on your left, pick up the chopstick on your right, eat, and then put down the left and right chopsticks, think, and go back to the top. That's a pretty, obvious algorithm. Well, pick up the chopstick on the left. Okay, suppose that every philosopher does that at the same moment. Okay, so this philosopher is going to take this stick. This stick will go to this one, that one, that one, that one. No problem. Everybody can do their first step. Now each philosopher tries to pick up the stick on the right, but cannot do that because that stick's already been picked up. And we've immediately got a deadlock problem. Because right now, nobody can make progress past this first step. They're all going to sit there and wait until they can pick up the stick on the right. And nobody's going to be able to do that because nobody will put down the stick on the right until they've eaten, which would only happen after they've picked up a stick on the right. So it's deadlocked. So that's not going to work. So you could try something like pick up the stick on the left, pick up the stick on the right. But we can put some conditions on here. If not available, put down the left and go back up here. So pick up the stick on the left if you can. If you can't pick up the one on the left, you just wait until you can. And once you have the left chopstick, try to pick up the one on the right. And if you cannot do that, then put down both chopsticks and go back up to the top. Okay, so how would that work? Well, each philosopher picks up the stick on their left, and then they each try to pick up the stick on the right, and this philosopher can't, so they put down that stick, and this philosopher can't, so they put down that stick, and so on and so forth. And now all of the philosophers are back to the beginning of their algorithm. Nobody's holding any chopsticks. We're back in the original state. And it's possible that, even though these things are randomized, all 5 philosophers could decide to pick up their left stick at the same time and then try to pick up the right stick at the same time. And theoretically, this could be a state where we have Livelock, where they're moving through their algorithms, but they're never getting beyond this point. So, who's got ideas? What else could we try to do to let these people eat successfully? Or are we just going to let these poor philosophers starve? Limit to one person at a time. Alright, cool. We got some ideas coming in. So first idea, limit to one person at a time. That would work great, right? That's basically taking these parallel operations and making them execute in serial. And if things are happening sequentially, right, if we take away the parallelism, we don't get into this potential for livelock deadlock, right? So we could say, okay, first this philosopher eats, pick up both sticks, put them down. Then this philosopher eats, pick up both sticks, put them down, and so on. Okay? That's a perfect solution. It's just that it's 1/5 as efficient as, if they could all somehow eat at the same time, which isn't possible. But that's a great first order solution. All right. Someone else was thinking of letting 2 people go at a time, and that you can also do, right? So for example, these 2 philosophers can both pick up their chopsticks and eat, and guaranteed they're not going to interfere with each other. So you could say, okay, both of you pick up your chopsticks, eat for a minute, put them down, and then these 2 could do the same thing, and then these 2 and these 2 and so on. And that's twice as efficient as going strictly sequentially. Not as efficient as we possibly could do, but that's more parallel, which is good. So that's another good idea. Wait at the start for a random time. Theoretically, this is supposed to be random. The problem is with randomness, it's possible that every time you flip a coin, it comes up heads. It's possible that even though they're waiting for a random amount of time, they might all at the same instant say, okay, I'm going to pick up my chopstick. Right? And it's a little bit what happens when you're walking down the street and you come up in front of someone, right? After a few iterations, you start to wait to see if the other person's going to move. And when they haven't moved, you suddenly jump over. But too often, they've decided to wait exactly the same amount of time and they jump over at the same moment, right? And it's the same thing as talking on a cell phone. You're waiting for the other person to say something, you give up and decide to start talking at the same moment that they've made that decision. And so, yeah, in practice, having these things be random is usually going to work well. In theory, it could still leave us deadlocked or livelocked. Use an ID for each philosopher and let every other philosopher pick up both. So this is another possibility, is if you identify the philosophers and have something in your algorithm which says, if you're philosopher A, do this, if you're philosopher B, do that. Right? That's another way to manage this, and that's a really good practical way when you're doing this in a programming situation. If you have control and you know what the total scope of threads is, you can do that kind of ID. And we do that somewhat in PA5, right? We have a client and a server, and we do different things based on those. Top left and bottom, yes. So that's a scheduling algorithm, right? Which also gets into a more general solution, which is to have a wait person who basically, like, tells people when they can pick up their chopsticks. Have a central arbitrator whose job is to make sure that everybody eats and nobody starves. And so they could say, okay, well, this philosopher can go first along with this one, and then when this one's done, this one can go, and so on. Make them take turns, yeah. So that's something that a wait person could do, right? Or if you have some sort of ID, you could number these, and you could say, okay, everybody who's got an even number can eat first, and now everybody who's got an odd number can eat, and so on. So you can alternate like that, and then rotate and continue. Yeah. So there's ways to deal with this. All right. And depending on the situation you're working with, some of these are more feasible than others. For example, if these are jobs trying to access, a printer and a scanner, we don't really have a way to control the time interval between which they're going to make these requests, how long they're going to wait if they don't have access to both resources, and so on. But a central arbitrator might work well in this situation, okay? That's basically where we start talking about daemons. So like a print server, part of what it does is it takes requests from multiple entities and it manages them so that one entity at a time gets access to the resource. And it can even do things like, say, if you're printing more than 5,000 pages, we're going to pause your job and let somebody else come in and print, and then we'll come back to your job. And these these sort of higher level examples don't really come up as much anymore, but if you go back to 60s or 70s or even to some degree the 80s, where computers were not something on your desk, right? They were a central resource. Everybody had access to one printer, and everybody had access to one plotter, and these things had to be shared. And there were issues where somebody would use a resource for 10 hours, and everybody else would be sort of backlogged waiting for that first job to finish. So these issues come up, right? So Deadlock and Livelock, two key issues here. And this is not something that that synchronization is necessarily well suited to. Okay, this idea of a synchronized block in Java lets us control access to a section of code. So we could synchronize on, say, this whole process, pick up the left and the right chopstick, so that once you start doing this, nobody else can do it. And that could work pretty well. But it starts to get into another idea, which is, we've talked about semaphores, right? We've talked about these flags that you can use, and you could manage this with semaphores, right? Your chopsticks are basically flags saying, is the left chopstick available? Is the right chopstick available? So some kind of thing that you can check and set. So that if you want the left chopstick, first you say, is it available? And if it is, you set a flag saying it's in use. All right, and that has to be an atomic operation, a read modify, right? And you could try to do both chopsticks like that, right? Are both of these available? And if they are, set both of their in use flags so nobody else tries to get them, and then go ahead and pick those up. But what do you do if the chopstick's not available? So you wait a random amount of time, but how long should you wait? So think about the shared printer example. You have a process that wants to send something to the printer. It checks the flag, and we're using a proper atomic operation to check and set the flag. Okay, so we check the flag says printer's in use. What do? We could say something like, while that flag is true, just sit here and spin. Just keep checking to see if that flag is true. And then when the flag is no longer true, so this is, wait for in use equals false, and then flag equals true, which is show resource is in use, and then print your stuff. All right, but this is really inefficient. Right, this is a very tight loop of machine code that basically says, check this variable, and if it's not equal to 0, branch back to this same instruction. Okay, so it's kind of like a branch if not 0 in itself. CPU bound. Okay, this will spike your CPU use meter. So often what we do is we say, while the flag is set, sleep for, I don't know, a microsecond maybe, so that we're only executing 1,000 of these statements per second, which is not too bad. But it's still a lot of CPU use, right? Now we could wait for half a second, and to print a job, that's not bad. But other things, a half second might be a really long time, right? If we're trying to control access to, something that sends messages out through the network, and you hit a key and you have to wait a half second for that key to get set, that's not acceptable. And this comes up all the time with event-driven programming, right? How does our swing setup work when we click a mouse, right? You click a button on your mouse and you jump into your mouse listener code. You type a character on your keyboard and you jump into this key pressed method in your key listener. How does that work? Well, there's something out there, which is responding to the change in state. But you don't want to do that by just sitting there continually checking. Okay, so this is called polling. We're back into like engineering 250, 270 now. Polling is where you continually check something to see if a condition is satisfied. So you want to know if a button's pressed, read the state of the button. If it's not pressed, read it again. If it's not pressed, read it again. And keep doing that until you read the state of the button that says it's pressed. Oh, okay, now the button's pressed. All right, but polling is inefficient. It's very CPU intensive. So in 250, 270 speak, the alternative to polling is to use interrupts. Okay, in Java or programming speak, this means being event-driven. So how do we implement that? How do we write code that doesn't sit here and just continually checks a flag? How does the mouse listener work? How is that code actually set up so that when something happens, your code suddenly gets called? So one way to do this is with something called a condition variable. And this is a general concept. Okay, there's condition variables in Java, but they're also in C. There's a POSIX version. Most languages have some form of support for this. So the idea of a condition variable is basically you have a pair of methods. One of them is basically saying wait for some condition to be true, and the other method is send a signal saying that this condition is true. And the setup would be you would have a number of threads, so think, processes that want to use the printer, and the printer's in use. So each of them would basically say wait. And they would set up a request to be woken up when this condition, which is the printer is available, is satisfied. And the daemon that's managing the printer, when it finishes the current print job, it would send a signal. And the operating system or the Java virtual machine or whatever is managing this at the lowest level will pick one of what could be a number of processes that are waiting for that signal and signal it. And say, hey, the thing you were waiting for just happened. Okay, but it'll only do it to one. And now this one goes ahead and it gets a lock on the semaphore, and it starts, printing. So condition variable, semaphores, mutexes, these are all things that you can talk about in an operating system course or a system programming course. And depending on what you're doing, you may never run into these, or they may be, your best friend for 6 months. Depending on what you're working on. Okay, if you're writing like device drivers, like low-level code that works at the kernel level and is managing interaction between the operating system and hardware, you're going to be doing a lot of this kind of stuff. If you're doing embedded programming, you're probably going to be doing a lot of this kind of stuff. If you're doing game programming, right, you're probably working at a high enough level that this stuff is being managed for you, just like in Java. We can say synchronized and not have to worry about a lot of this stuff. But it's useful to know what's going on at the lower levels, right, because it'll affect us. All right, let me show you another interesting thing that happens in Java. So here's a thread, okay, called my thread. Really simple. It's got a class variable called flag. It's just plain old integer. I initialize it to 0, and then I say, well, flag is equal to 0, and I just sit here and I spin. Okay, so I'm polling. This is the thing I said we don't want to do. I'm just sitting here and I'm just waiting. You know, is it 0? Is it 0? Is it 0? As soon as it's non-zero, I'm going to print out goodbye. Alright, so here's a main program. What does this do? This constructs a my thread and starts it. Okay, so after the start, the thread is sitting here in this loop. Waiting, waiting, waiting. Alright, my main program is, you know, constructing a scanner on standard N. It's going to say hit enter to set the flag, and it's going to wait for me to hit the enter key or type in anything. And when I do that, it's going to say mt.flag equals 1. Okay, MT is the name of the thread, so that's going to come in here and it's going to set this flag variable to 1. Okay, and then it's going to wait here and say hit enter to exit and wait for me to hit an enter, and then it's going to exit. Alright, so what's the setup? I'm going to run this program. The thread is going to start and wait for the flag to be set to 1. This should say hit enter to set the flag. I'll hit enter, the flag should get set to 1. It should say hit enter to exit, and meanwhile the thread should come out of this loop and say goodbye. And then when I hit enter over here, this program will just exit. Alright, so I'm going to run this. It's going to say hit enter to set the flag. This should set the flag to 1. Hit enter to exit, and not only did our thread not say goodbye, but my main program did not exit. So this is a weird looking thing. And, you know, I can keep hitting enter and it does not matter, right? And if I look, this process is CPU bound. Using 100.3% of the CPU, right? Because it's sitting there in that loop and it's waiting for this flag to get set, but we already set it to 1 and it didn't notice. Alright, so let me do something really strange. Let me just print an empty string here. So inside the loop it's going to sit there and it's just going to print an empty string. It's not going to do a new line, so we're not going to see anything on the output. Okay. So I hit enter to set flag. I do that, my thread said goodbye. This says hit enter to exit. I do that and my program exits. Everything worked as we expected. So just adding this bogus print statement seemed to make our code work. And that's kind of a bummer. If you were actually trying to do this and we're trying to debug, you might print out the value of flag in here, and suddenly your bug is gone. And you're like, oh, I guess it worked fine. So you take that print statement out, and you turn in your code, and I try it, and it's doing the buggy behavior again, right? This is one of the things that happens with threads. Okay, so if this thread is running and it wants to touch something, you know, in your original main method, that's pretty safe. But you can get into these weird situations, and this is deliberately a pathological example. And in fact, there's nothing magic about the print statement. I could put other things in here that would make this thing work. But here's what's happening. This is a really, really tight little loop. Okay, it could be one statement if this was coded into assembly language. Right, branch if not 0, flag, comma, current location. 2 statements on a PIC processor. Move FF flag, comma, W and branch if not 0, previous statement. Really, really small loop, okay? And small loops get optimized. Now flag is a variable sitting up here. It's an integer. It's a location in memory, right? But it's not necessarily a location in memory inside this loop. Probably what the compiler would do is take this location in memory that we're calling flag and copy it into something like a register. Okay, so depending on the CPU that you're executing this on, and for Java it's executing on a JVM, but you know, if this was written in some other language, it would be running on a PIC or an Intel or an ARM or something. This location in memory might be cached locally. Okay, in other words, every time that we check the value of flag, we may not be going to the actual spot in memory where this variable is stored. We might be reading a copy of it that we've made. Why? Because accessing memory is expensive. Accessing a register is fast. And so this code thinks it's doing the right thing. It's made a copy of this register before it started the loop, and now it's just checking that register value to see if it's equal to 0. And the compiler, you know, faithfully believes that if this is supposed to be non-zero, something's going to happen in here. And if anything in here references flag, it's going to change the value of that register. But over here, when we say main thread.flag equals 1, this doesn't know that our thread is sitting in a loop and the copy of flag has been copied to, I don't know, register 7, and that register 7 is being checked. The only thing that this knows is there's a class variable named flag, right? Let's find where that's stored for this instance MT. Let's set that equal to a 1. And so even though, you know, we're clearly saying set the value of flag to 1, this loop is not noticing. And it's basically a caching issue. It's storing a local copy of flag instead of reading it out of memory. Okay, so there's something we can do to change that behavior. We can say flag is volatile, which means it might change unexpectedly. And in particular, what we're saying is, you know, another process in a different thread might change the value of this flag. And by saying it's volatile, this loop will actually go back and read the value of this variable from memory instead of using a local copy. And that's enough to make this code work again. So you can use the volatile keyword, but you know, a better option perhaps is just not to do this kind of direct access across threads, right? So accessors, mutators, control your access to these things instead of just kind of reaching into the middle of another thread and saying, here, let me borrow that object, I want to change the value of a variable. Okay, but depending on what you're doing, sometimes volatile is a good keyword to use. Alright, so that's just something to keep in mind. Usually doesn't come up, but it's another aspect where even though we're at a pretty high level being in Java and working with swing and so on, sometimes a knowledge of what's going on at the lowest level is actually relevant here. Alright, I also want to talk about another way to implement threads. Okay, so we've been talking about making a thread by saying, here's my class, it extends thread. There's actually another approach we can use, which is to implement what's called a runnable. And it's more or less the same thing in the end, but it looks a little different. So here's what I'm going to do. I'm going to make a myThread3, and I'm going to say implements runnable. Okay, implements is a keyword which says, somebody has defined what a runnable is, what types of methods are in a runnable. Runnable is basically a blueprint. So a blueprint for a house says you gotta have a front door and you gotta have a entranceway and you gotta have a window or whatever, right? So a runnable basically says you have to have a run method. Okay, so I'm saying class my3 implements runnable, and here's what I'm going to do. I'm going to just say public void run, and I'm going to put a run method in here, and it's going to be the same thing that we've done before. We'll just print out, let's just print out 20 numbers. Alright, so how do we use this? I did not say extends thread, but we're going to turn this into a thread. So I'm going to say my thread 3, I don't know, call it ant equals new my thread 3. And I'll make some other, I'll do a bat and I'll do a cat. Back to our linked list code. So I got 3 my threads, okay? And each of these my threads is just a class that I've defined, but I've said it implements runnable. Although I misspelled implement. Alright, so now I can say thread t1 equals new thread ant. So I'm going to construct threads on the fly out of these classes, out of these objects that I've said implement runnable. And now I'm going to start these threads. So if I run this, I've got my expected behavior where one of these threads said 0, 1, 2, 3, 4, and then a second thread kicked in with 0. There's 5, 6, 7, 8, 9, 10. A second thread kicked in with 1. Then our third thread kicked in with 0, and so on. And over here we've got multiple threads running at the same time. So this is another way to do threading. But the thing that we're using to make our threads is not extending thread. Okay, instead we're saying implements runnable. Why would we want to do this? Because in Java you can only extend one class. So if we wanted to make something that, say, extended, I don't know, a JPanel, for example, right? We could not also have it extend a thread. You're limited to only extending one class. So we could extend a JPanel but implement runnable, and then put a run method in there, and then we can construct a new thread where the constructor is this thing that extends runnable, right? And we can put whatever we want in this class. And then we can call it start method, and the start method is happening because thread start means call the runnable, call the run method, right? And these things have run methods in them. But we still get the action because we're constructing a thread with ease of having them call the run method in separate threads, separate processes. So these things are executing in parallel. So 2 different ways of making things happen in parallel. I find extending threads to be easier, just because I just construct these and then I can say ant.start, bat.start, and so on. But some uses prefer using implements runnable instead. But it doesn't change any of the issues of what you actually do with these threads once they're running, how you communicate back and forth, and so on. All right. Questions on any of this? All right. Well, we got 3 minutes left. I'm just gonna leave it there. How much knowledge of threads will we need for the final? I would like you to understand the concepts related to threads, but you also might be asked to do some coding because you've done threads for PA5. But basically, you know, the notion of constructing a thread, you know, something that extends a thread and then calling the start method and knowing that that executes the run method. Just sort of the basic use of them along the lines of what you had to do for PA5. I'm not going to ask you to get into anything terribly subtle or any of these weird situations with volatiles or dealing with deadlock or things like that. Those are good theoretical topics to just have seen so that the next time you see them they're not totally a surprise. But for the exam, just basically know how to construct threads, how to start them, and that's probably fine. Alright, cool. Well, have a good weekend. I do have office hours at 3 o'clock today, so if you want to talk about your PA5 code, we can definitely do that then. Otherwise, have a great rest of the day, have a great weekend, and I will see you on Monday.